going to present some back to basics on chemical analysis of solution and calculation of speciation and solubility of minerals using PHREEQC. So first, when you want to analyze a solution and the speciation of the solution and the equilibrium with minerals and gases, you need to analyze the more parameters and elements you can. So you need particularly in situ parameters such as pH and temperature, which are the most important ones, but you can also measure the conductivity, the oxygen concentration in the water, and UV depth, etc. But you need absolutely pH and temperature. You also need to measure the major cations and anions of your solution. So not only calcium and magnesium, but also chlorine, sodium, etc. And you can also analyze traces elements and nutrients, and particularly if they are really important. And also alkalinity or dissolved inorganic carbon to constrain the carbon content of the solution. So NEA did a really interesting Google sheet, which is here, where you can find all the method you can use to analyze all the elements of a solution, where you can find those type of methods, the contact, the principal contact of the person who is in charge of this, and over information. So you can see that you have major and trace element by ICP, for example, or you can have different colorimetric methods to have mostly the nutrients, so phosphate, nitrate, etc. So you have all these information here. And so what's it important is to make sure that all your analyses are good. And to do that, you can calculate the charge balance in percent of your solution. It means that your solution needs to be in equilibrium. So you need to have the exact same charges between the anions, and the cations. So it should be less than 10%. If you have more than 10% of differences between the cations and the anions, it means that you have a problem with one of your analyses. So you can find which one is wrong. So I just prepared just 1 or 2 slides on alkalinity in particular, because we had some problem with Juliette and Ea these times to measure the alkalinity to constrain the carbon content of the solution. So just a reminder, so that you have 2 types of alkalinity: the total alkalinity, which correspond to the excess protons of your solution, which is not neutralized by the bases which are in the solution. So basically it means that you have the pH, the carbonates, but also the borates, phosphates, etc. And to analyze this alkalinity, you need to do a titration with a strong acid like HCl or sulfuric acid. And so you need 5 to 6 ml of filtered solution, but usually it's better to have 10 ml to do the titration. And you add a strong acid to your solution and make the pH change. So to had the equivalent points where you had finally neutralized all the the excess proton, the free proton you have in your solution. So I'm gonna show you next. And you have also the carbonate alkalinity, which is only the part of this total alkalinity, which is due to the carbonate species. So this is the same titration, except that after you put all the acid and in your solution, you make the CO2 produced by the solution degassed, and then you put a strong base in your solution to go back to your initial pH, and then you recover the, when you do the difference between the total alkalinity and the alkalinity you have left, this is the carbonate alkalinity you measured. And it must be measured as soon as possible after the sampling. It means that if you have a water stored somewhere in the laboratory for 2 years, it could change because the pH of your solution can change also. You cannot degas CO2, so you have to measure the alkalinity as soon as possible. So this is the graph I was trying to explain just before. So when you have a solution with an initial pH here, you had strong acid until you had a really acid pH. And thanks to that, on each step, you can calculate the Grand function, which is here in C2, and calculate a point, an equivalent point where you have added enough acids to compensate all the protons which are free to compensate all the bases which are able to neutralize protons. So when you calculate this equivalent point, you can calculate then the alkalinity, which is just the volume of acid you added on the volume you had at the beginning, so the V0, multiplied by the concentration of the acid you added. So this is really simple. You can do that at the IPGP if you want, because you need a closed system. And that's it. And if you don't have the alkalinity, you can also use the DIC, so the dissolved inorganic carbon, which is another way to just measure the carbonate in your solution and to have like one constraint on your carbon for the modeling. So this is typically what I put in PHREEQC, but you can use another system, another software if you want, like Chess or Visual Mintech. This is basically the same. Just so you need for PHREEQC to use a database. So in your database, you will have all the reactions used to calculate the speciation of your solution and most of the part of the minerals existing in most of the systems. So there is different database available. It depends what you want to do. The one which is here is for me the most complete one. But you have specific. I put there here. You have specific over database like PHREEQC, which is specialized in saline solution. So if you have really saline solution, you have to use PHREEQC and not this one, which is not, not really good for that. But you have different. You can use also the database of Visual Mintech. They are also available for PHREEQC. So yeah, you have different type of elements available, temperature, minerals. So it depends. You can check the database before doing your modeling. So then you put all the parameters and chemicals you have in your solution. So basically pH and temperature. I already said that. And then all the major elements. The trace element, they don't play a great big role on that. So and so with the pH and the alkalinity, you can estimate the carbon content, but you can do the same with the pH and the DIC. You will have an estimation of the alkalinity. So that's why you can, and if you have the three parameters, this is really interesting to check if you obtain always the same results, because usually it's not really similar. And when it's the case, you have to find which of the parameters is the most useful, the most relevant one. And then when you do that, PHREEQC will calculate all the speciation of the species in your solution. So based on the calcium concentration you told you enter, it will calculate all the different speciation of calcium in your solution, for example, based on the different equation of equilibrium of reaction between the phosphate and calcium, phosphate and calcium and sulfate, etc. It will give you, it will calculate the activity coefficient of all the species you have. So based on this equation, where Z is the charge of the element you're analyzing and E the unit strength of the solution. And these coefficients will help you to calculate the activities of all the species in your solution. And the activities are equal to the coefficient multiplied by the concentration in molar of the element you're considering on the reference concentration, which is equal to 1. So, and it's also calculating all the reactions of equilibrium with gas and minerals they have in the database. So for example, for the carbonates, it will calculate based on the equilibrium coefficient of the reaction they have in the database, the reaction of production of carbonates. So K, the solubility coefficient of this mineral is equal to the activity of carbonate on the activity of calcium and carbonates. And it's given at one temperature and pressure you define in your solution. So, and the activity of solids is equal 1. So basically 1 on the products of the ions in your reactions. So it will give you also the saturation index of all the minerals and gases you have in the database. So at a given pressure and temperature. So if I can show you what's it look like. So basically this is, in green, this is all comments. So don't look at that. So you have the database here and then the solution. This is exactly the same I showed just before. So all the elements, the units I'm using, the pH and the temperature. And then, so this is for BG11. And then this is the file you have, the exit file, the output file. So you have the solution I wrote. Then the modalities of all the elements I put in the solution. And then you calculate. So you can say to him, fix the pH or not, but yeah, the pH hasn't changed. The activity of water is 1. The unit strength is using to calculate the activity coefficients, the total alkalinity, temperature, and you see here the charge balance. So 0.09, this is perfect. If it's more than 10, again, you have a problem somewhere. So it means that your solution is not in equilibrium considering all the charges. So you forget something. And then you have all the speciation of your solution. So all the species you have the total calcium, total chlorine is given by me, but is calculating all the different elements we have in modalities, in activities, in logarithm. And then, yeah, all the saturation index of all the minerals and gases you have in the database available. So it's possible that something is missing. You can add it in the database if you want, but usually it's pretty complete. So for those of you who don't know what is the saturation index, it's just the logarithm of the ion activity product you have in your reaction on the coefficient of solubility of the reaction you are considering. So for example, for the calcite we have seen just before, it's the logarithm of the activity of calcium and carbonates on the solubility of the calcite. And for gas, the saturation index, which is given in the table, it's not saturation, it's more that the pressure of the gas you have in equilibrium with the water. And you have also uncertainties associated with this parameter. So we don't forget that 5% uncertainty on element concentrations you consider, calcium and carbonate, is equivalent to 0.02 units in saturation index. And the same for the pH. If you have reactions with pH somewhere with protons, you have to add 0.1 unit of uncertainty for 1 proton in your reaction. So when your saturation index is positive, it means that you are super saturated, oversaturated in respect to with the mineral you are considering. But it doesn't mean that it's present. It just means that if you have this mineral in your solution, you won't dissolve it. You will be able to precipitate if you can, but it doesn't mean that it's present because you have also kinetics and uncertainties on these values. So you always be aware of that it's not saying what is really in your solution. It's just a clue. At thermodynamic equilibrium, if you have a saturation index positive, you can precipitate, but not dissolve. If you are negative, but the mineral is present, you will be able to dissolve it, but not to precipitate. And if you are equal to 0, it means that you are at equilibrium with these phases. So to finish, you have different way to represent the solubility and the stability of the minerals you have in your solution. And the first one is this type of diagram where you can find the stability domain of the carbonates, like aragonite, hydromagnesite, and brucite, depending on the carbonate and calcium and magnesium concentration. And basically, when you do this type of diagram, the lines here are just the equilibrium between the two phases. It means that the limit between the aragonite and brucite, for example, here means that if you write the reaction to produce aragonite from brucite, you will need to add calcium and CO2, and you have a coefficient, a constant of reaction associated with this reaction with a value. So you can just construct this type of graphic like this. But for example, in some system, it doesn't help you to explain why you have this type of mineral and not another. For example, here you have sediments of Alchichica, and in these sediments you have both aragonite and hydroanezite, and in this type of graph, you can only see that you are close to the border between the two minerals and more in the domain of aragonite. So you cannot explain why you have both the minerals. So another way to represent your data is the solubility diagram. And here the lines are the solubility lines of each minerals, each carbonate you can find. So calcite, aragonite, monohydrocalcite, the ACC, and the amorphous magnesium calcite. So it represents the calcium or the magnesium concentration as a function of the carbonates. So, and basically the lines are just based on the solubility coefficient, the solubility constant of the reaction producing the mineral. And you can see here that in most of the lake, of Mexican lake, where you can find a lot of carbonates, different types of carbonates, you are basically oversaturated in aragonite, calcite, and more hydrated, more soluble phases like monohydral calcite and ACC. So, and just to show you why it can be important and really interesting to plot this type of graph, I choose this example. I found a paper of Purstaller in 2016, where they did some experiments of precipitation of magnesium calcite, and they monitored with Raman the precipitations in the solutions. So they showed that they precipitated in the solution first the magnesium-rich ACC, and then it transformed at some point in magnesium calcite. And they followed all the solution with Raman. And when I plot those data in a solubility diagram I showed just before, you can see that you can also follow the same reaction of producing ACC from T1 to 25 minutes. And then when it turns to magnesium calcite, you can see that the solution is not anymore in equilibrium with ACC. It's just different. You are in equilibrium with different carbonate phases, which are less and less soluble. And then at the end, they have magnesium calcite, and we are close to monohydral calcite. So well, that's. I think that's a really interesting way to follow what is precipitating in the solution, because the solution is always in equilibrium with the, not always, okay, but you can follow what is controlling. If you have a really high precipitation of minerals in your solution, it will have a consequence in the solution chemistry, because this is linked to. Voilà.
Merci beaucoup, Elodie.